workshop results. It's really amazing that it's sixth, right? Which means it's the eighth workshop altogether. The founder sits right there, Jordan Cohen. And today we have two teams. One of them, the Mandarin-English information team, and then another is the Mandarin pronunciation team, which will be in the afternoon. They will tell you what they came up with. As you see, they are overwhelmed with technology, and we are all overwhelmed with technology. During this presentation, there will be a presentation by Wycliffe Law proposing continued research in this area. Such presentations of continued research will also be presented tomorrow. I think the Mandarin pronunciation does not have a proposal of that type. So, without further ado, I give you Helen.
Hello? Can you hear me? Is that okay? So good morning. I'm happy to be here with my team. My whole team, I guess almost the whole team is on stage today, and this presentation will be a team effort. We're the May team, and May stands for Mandarin-English Information, investigating translingual speech retrieval. That's our main task for this summer. And the Chinese character you see here is pronounced Mei, so it has the same pronunciation as our acronym, and it means beauty. It also refers to 美国, which is the United States, the beautiful country. And indeed, in order to tackle this language pair, Mandarin, Chinese, and English, we need people from both sides of the globe. And this is reflected in our team composition. My name is Helen Meng. I'm from the Chinese University of Hong Kong. And I'm here with my graduate student, Wycliffe Lo. We also have Erica Grams from Advanced Analytic Tools, Sanjeev Kudampur from Johns Hopkins University. We have strong showing from University of Maryland, Gina Laveau, Doug Ord, and Doug's students, Jen Chang Wang. We also have Pat Schoen from the DoD, and Shimin Wang from Taiwan, Academia Sinica, and his student, Berlin Chen from NTU, National Taiwan University. And last but not least, we have our undergraduate, Karen Tang from Princeton University. Here is the outline of our presentation. We'll first motivate the problem, then we'll provide some background information about our investigation. And in this project, we're proposing a new paradigm for translingual speech retrieval that we refer to as the multi-scale paradigm. And the multi-scale notion actually permeates the whole, our whole system throughout, from query processing to document indexing to retrieval. Then we'll tell you what we call the perfect retrieval myth, and we'll present some experiments and findings, and finally conclude. So you might be wondering why translingual speech retrieval is an interesting task. Well, first of all, one may note that Compaq has this project called SpeechBot, where you can go on their website and you can type in a text string in English, and it will retrieve some audio files for you from a large database of different audio clips from various TV shows or news broadcasts. So as we can see, monolingual speech retrieval applications are crossing the threshold of practicality. And our last check with Real.com in February of 2000 shows that amongst all the internet accessible radio and television stations, in fact, over a third of them are in languages other than English. So it seems that the natural next step in pushing the technology front here is to move towards translingual speech retrieval. So then you might ask, well, why this particular language pair, which is English and Mandarin Chinese? Well, it takes very little to convince me, because I'm from Hong Kong and I speak both. And in fact, we also speak Cantonese, which is another major dialect of Chinese. But here is a piece of statistics from Global Reach that might help justify why we should focus on this language pair. It says that by the year 2005, the two predominant languages used by the internet user population are in fact English and Chinese. So perhaps we're actually tackling a good language pair right now in this project. So what is the May project about? The May project is about cross-lingual and cross-media retrieval. This is the big picture. We have English text queries, and in fact, we're using a query by example type of retrieval where the query is in fact a whole news article. It's a long query which is the entire news story. Our document collection are in audio form. These are Mandarin news broadcasts. So how do we facilitate retrieval between English text queries and Mandarin news audio? Well, we use a bunch of technologies, the three key ones being English to Chinese translation, Mandarin audio indexing by automatic speech recognition, and then the translated query, which is now in Chinese, and the indexed audio, which is now in some form of text, is fed to a retrieval engine which produces a ranked list of Mandarin spoken documents. So one could conceivably imagine that in the future, our May project can be further enhanced by technologies such as which facilitate interactive refinement between the user and the machine, and technologies like speech-to-speech translation, which can translate the Mandarin spoken documents into English spoken documents. So a user, in fact, does not really need to know Chinese. He can search Mandarin audio documents by inputting information in English, and he also receives information in English. But in fact, he's searching Mandarin. So before I move forward, I'll show you a concept demo. Actually, Karen, our undergraduate member, will show you a concept demo.
Okay. All right, so here's an example of how we could conceivably use, I'll just leave this on the table, how we could conceivably use the research that we've done in a real-world application. So let's say we're online or reading some kind of news source, such as the New York Times, and the Clinton-Jiang debate catches our attention, and we're reading it, and we're realizing, well, the American media is portraying a rather optimistic view of the situation. And what might cross our mind is, well, what is the Chinese media portraying to its people? Is it share the same view, or does it disagree? So one way to do this, we can just, with the click of a button, we can send this article as a query to our system, and what we get from it would be a list of Chinese broadcast audio which would be most relevant to this article that we sent to our system. But before we see the results that our system would return to us, it's important to realize what we're actually sending to our system. And the key point is that we're actually sending an article instead of an entire article rather than keyword query. So what this means is that our queries tend to be a little longer, and this type of searching is known as query by example. But by doing so, we've also added a layer of complexity to our system, in that our system now needs to be able to ID certain types of terms. And we've color-coded our articles such that the green represents phrases, multi-word phrases. The blue is named entities such as people names, locations, organizations. And the red numbers, which you see, like in the second article, the 13 days in 1996, right here, are another type of term that our system needs to be able to first identify and then deal with them appropriately. So having said that, we can see what our system would return to us. Just kidding. Just kidding, yes. All right, so what you see here is we've decided to return the top 10 of what our system thinks is the most relevant Chinese broadcast text version that is related to the query that we passed to it. And because a fundamental part of our system is the audio portion, the fact that we're searching on audio rather than just text, we could potentially listen to each of these broadcasts. So a sample one, which will take, since we're due to technical difficulties, and a sample broadcast file would sound something like.
前苏联的格鲁吉亚共和国当局目前进行谈判，争取。
So something like that. So having gotten this list of results, we could either read the broadcast news, or we could either listen to it, or alternatively, we could also read the translated version, because we read the article in English and we'd like to get the results also back in English. So there's an alternative where you can click and read the translation, which if we were online, I would show you. So this is just an overview of a potential usage of our research.
So Karen has shown you what the May system might be able to support, what kind of search the May system may be able to support. It's English text queries searching for Mandarin audio documents. Now, why is this task difficult? We have identified two prevailing problems in what we call cross-lingual spoken document retrieval, CLSDR. The first one has to do with translation. So first of all, we have to translate the query from English to Chinese. And in fact, during translation, because we're dealing with news, which covers a broad range of topics, conceivably, oftentimes you'll encounter out-of-vocabulary words for translation, words that our translation resources do not know of and therefore cannot be translated. On the other hand, there are also words that have lots and lots of translations. And under those situations, we have to find ways to intelligently pick the correct translation for the context. The second problem is a recognition problem. On the audio side, again, we're dealing with news audio, so lots of different kinds of words can be said can be found in the audio. And given a recognizer with a finite vocabulary, it is bound to encounter out-of-vocabulary words. These are words that lie outside of the recognizer's vocabulary. And hence, if we're indexing the audio by means of words, by word recognition, there will be chunks of audio where these out-of-vocabulary words occur that the recognizer cannot produce a correct word hypothesis for. The other side of the problem is, well, if the recognizer cannot produce the correct OOV because of the nature of OOV for that chunk of audio, then it will tend to substitute words that have similar acoustics. And hence, we will get a different set of words for that chunk of audio. Or the mismatch may not just be due to OOV. In fact, many words are acoustically confusable. Even for in-vocabulary words, they might be acoustically confusable with one another. So therefore, we have to face the problem of speech recognition errors in audio indexing, which may be due to OOV, but in any case, it will be due to acoustic confusions. So we're scratching our heads and we say, well, what is a possible solution that one can try to use to address these two problems? And we believe that perhaps subword units may help us. So for example, in the case of translation, oftentimes words that cannot be translated are named entities, such as Northern Ireland. Right? The actual Chinese translation for Northern Ireland is a 4-character word, and it is pronounced as Bei Ireland. Now notice that actually Bei means north, and it's a semantic translation in this case. But Ireland, in this case, is transliterated into something that sounds like what it is pronounced in English, Ireland. So in fact, it is a transliteration. So hence, there's a potential solution here. Maybe for words that we cannot translate, we can try to transliterate in the phonetic space. Now, in terms of the recognition problem, we can also try to think of subword units. As an example, consider the word Iraq. I borrowed this example from a BBN demo on Oasis, and we saw that we're not sure whether Iraq was in BBN's speech recognizer, but instead of seeing it, we heard Iraq, but instead of seeing it come out of the speech recognizer, we saw Iraq. And in fact, as you can see, these are very confusable acoustically. Now, in the May project, we're not dealing with English speech recognition, so we're not faced with this problem, but this problem serves as an illustration for the problem that we actually face. Now, I'm going to move this example into the Chinese domain, but before that, I'd like to talk about a few things related to Chinese or Mandarin Chinese speech recognition. Mandarin Chinese is a rather interesting language because with a compact inventory of 400 syllables, we can actually achieve full phonological coverage. So in fact, if you give me any audio in Mandarin, and as long as it is speech, right, spoken Mandarin, I can fully index the audio stream using these 400 syllable units. Now, the other side of it is the 6,800 characters that can be used. Now, this is in text form. With 6,800 characters, you can actually achieve full textual coverage in written Chinese, and this is for the GB-coded Chinese. If it's Big 5 coded, then the number is a little bit bigger. Now, when I say full textual coverage, that means you get full character coverage. You give us any newspaper, and with these 6,800 characters, we can recognize all the characters in the newspaper article. And each character is pronounced as a syllable. And the mapping between character and syllable is a many-to-many mapping, so there's a certain amount of ambiguity there. Now, from these characters, we can actually generate an unknown number and probably an unlimited number of Chinese words, where each word consists of 1 to several characters, and the character combinations can create different meanings. So there's an ambiguity in word tokenization, which means if you give us a sequence of Chinese characters, we can segment them in different ways, leading to different word sequences. And the different segmentations can actually all be legitimate sequences, but because they chop up the the character sequence in different ways, we get different word sequences which mean different things. So knowing that, let's consider the example of Iraq, but now let's consider it in a translingual setting. So in the query, let's assume we have the word Iraq, and it gets translated with maybe a pretty good translation dictionary to Ilaka, which is the correct translation for Iraq. So now we have a translated Chinese term, Ilaka, on hand. Now let's look on the document side. If in our recognizer's vocabulary, we have this word Ilaka, then there's a good chance that we will recognize it, or a decent chance that we'll recognize it. And if we use the translated term Ilaka to retrieve the recognized term Ilaka, then there shouldn't be too much problem because they match at the word scale, at the character scale, and also at the syllable scale. However, if, for example, our recognizer does not have the word Ilaka, then given that we have a decent recognizer with maybe 6,800 characters, which is not a whole lot for a recognizer's vocabulary, it is possible for our recognizer to piece together 3 mono-character words, I, La, Ke, which means totally different things, but it sounds exactly the same as Ilaka as a single 3-character word. Now, if we're retrieving on the word scale, that's not going to work. However, if you're allowed to use, let's say, a syllable trigram as a unit for retrieval, then you can see that this is a translated syllable character trigram. And if you lump these 3 characters together to form a character trigram, you're still fine, right? Or alternatively, you can use 2 character bigrams. Here we can have 2 character bigrams, I, La, and La, Ke, and we call them overlapping character bigrams because they share the middle character. And if we're allowed to retrieve using character bigrams, we're still okay, right? So, or character monograms, we're still okay. So characters is okay, and similarly, the syllable is okay because the syllable pronunciation has not changed. Now, Then we have to face the problem of homophones. This is the case where two different characters are pronounced in the same way. So this is E, which means she. This is E, which means one. They're pronounced the same way. They're both E's. Now, in this situation, we still hear ilaka in our audio stream, and the recognizer may produce 3 single character words, but this may be favored because this has a higher unigram probability. Now, one can imagine that in such a condition, the character trigram will not work because the first character is different. But the second character bigram will still be okay, which is why here we have a triangle which signifies a partial match. Now, on the syllable end, though, we're still fine because it's a homophone. Now, this is an example of the problem of tokenization ambiguity. This is still ilaka, except it consists of a single character word followed by a 2-character word. So in this particular case, you can see both word and characters will fail, but syllables will still be fine. And finally, here's where we have or maybe this is the next to final example. Here's where we have a syllable recognition error. And in this particular case, syllable retrieval based on syllable n-grams will have a partial match. This is where we can partially match ila over here, but la-ka becomes la-de. And this might be favored because de is a syllable with a very good unigram probability. And of course, when all fails, when we have 2 syllable recognition errors, then nothing will work. Right? So essentially, this series of examples show you that, in fact, there are certain advantages of using subwords for retrieval. Because there are cases when words don't work, but character n-grams will work. And there are cases when both words and character n-grams don't work, but syllable n-grams will work. Right? In other words, some of the pros for using subwords for retrieval is, for character n-grams, it is robust to word-level mismatches due to different tokenization. For syllable n-grams, it is robust to word or character-level mismatches due to homophones. And in fact, both support partial matches for retrieval. And the downside of subwords is, obviously, subwords do not contain as much lexical knowledge as words. And we all think that lexical knowledge is important for retrieval. So perhaps this leads to, this is a good time to introduce what the point of the May investigation is. Here in this project, we're investigating the use of a multi-scale representation for cross-lingual spoken document retrieval. And by multi-scale, we're referring to using the word level, the word scale, as well as the subword scale, units from the subword scale level. And as I mentioned previously, this notion of multi-scale then permeates our entire system, right? You remember earlier in a picture I showed that we're working on machine translation on the query side, we're working on audio indexing on the document side for the purpose of retrieval. So because of this focus in our investigation, we're looking at possible ways to perform multi-scale query translation, multi-scale audio indexing, and multi-scale retrieval.
Thank you. So each of our speakers today that's upcoming will talk to you about evaluation results to show you how the technology that we've been working with has performed. And so what I'd like to do now is talk to you about how we know the reliability of the numbers that we'll present to you and what those numbers indicate. So to go back to Karen's example, here is an example query. President Bill Clinton and Chinese President Jiang Zemin. I had to say that. It's the only Chinese word I know. And so this is one of many queries that we have by example. So this is given to us as a document. And this document, we're told, is the query by example. Now, we could have been given this one, or this one, or that one, or that one, or that one. And this is what makes this a little bit of a unique task. This is different from a query that a user gives you. If you go back to ask the user, could I have another query, please? You might get a variant of the same query. Whereas here, you might get a quite different article here, here, or here. So one of the interesting questions is, if I give you a different example, what degree of variability does that introduce? And how do we guess how we would do on the next example you gave us? Because that's really the question. The question is not how did we do on these examples. The question is how will we do on the next example? It's not even how will we do on the next example, how will we do on the next topic? So we want to know how we'll do on a topic that we haven't seen yet, on an example you haven't chosen yet. That's what we're trying to estimate for you. Now, what can we do? Well, we can only look at the data we have. So we take one system and another system. And we'll focus first on the first system. And we ask, which documents does it find? So imagine it finds this document, and this document. Now, because we're using the topic detection and tracking collection as a source of examples and as a source of Mandarin audio to search, the audio here is from the Voice of America, assessment has already been done at the Linguistic Data Consortium to tell us this Mandarin audio news story is relevant, this one is, that one is, and the others are not. That's the expensive part of this test collection, is finding out which ones are not relevant, right? Because you have to listen to all of them. So we have complete exhaustive relevance assessments for 17 different topics for many different examples. For many different exemplars for each topic. Okay, so that's the setup of the problem. And when we run this through, well, I'll tell you a little bit more about the collection first. So we have 17 of them, 17 topics, variable number of exemplars. Could be 3, could be 12, could be lots more than that. We have 2,000 stories that we're trying to retrieve from. And that's in our development collection, which is from the second topic detection and tracking evaluation. We ran all of our development work on that. And then we had a Tiger team go off at the end and run blind on this collection. So they took exactly the same techniques we'd been developing, the same parameters that we had tuned, and tried it on a completely different collection. It's a different set of 3,000 stories. It's now 56 topics, again, a variable number of exemplars, and we have the exhaustive relevance assessments to work with. So that's the entire collection, and the question is, did we learn on these 17 something that transferred to those 56? So that proof's in the pudding there. Now, in order to compute the evaluation, we need to abstractly model the task of finding documents that a user wants to see. So we start out with an exemplar, we start out with the news, we put them into a system, and you get, this is important, a ranked list. You don't get a list that you can compute the recall and the precision of, because it's not a fixed list. If you go further down the list, you expect your precision to decay, your recall to increase. So we want a metric that tells us how good is our ranked list. Well, here's an example of a ranked list. These are the first 6 documents. Our ranked lists have 1,000 documents in them. So we take the exhaustive relevance assessments, and for each of these documents, we check and see if it's relevant or not relevant. So here, the first one's relevant. These 2 are not relevant. If we only look at the first one, our precision is 1, but our recall is quite poor at this point. Our recall is increasing as we see more documents, but you expect the precision to decay as you go down the list. So what we want is we want a metric on this list, right? After we've applied the relevance judgments, we want to know, is this a good list? Is that a 0.7 or is that a 0.4? That's what our number describes.
Excuse me, could you put it better?
Yes, sir.
The article or the documents on the left-hand side, they all concern the same thing?
Well, we have presented an exemplar, and then we have gotten back these articles. And our system has claimed that that's the best one, that's the second best one, that's the 6th best one, down to 1,000. But now we have to have a human look. So the human looked before we got here.
This comes from LDC.
That's right. So the ground truth is provided.
Or not is the judgment of those judges.
That's correct. Okay? And so now we have this list of relevant and not relevant, and we want to compute a metric on that. So here's the metric that's usually computed. The precision, as I've told you, will decay as you go down the list. So here the precision starts out being very good, and you get this sort of classic down into the right decay pattern. The recall, on the other hand, as you go down the list, improves. So the precision is the density of relevant documents. The recall is the degree of comprehensiveness of your search. So as you look further down the list, it's more comprehensive. Now, if you'd like to compare two of these curves, then you'd like to be able to find a single figure of merit. Well, if it were a very good system, it would be all the way over here and then down. If it were a very bad system, it would be all the way down here and then over. So the area under the curve is a reasonable metric for saying this system is better in some sense than that system. Of course, a curve that goes like this and a curve that goes like that will have the same area, but of course very different characteristics for a user. However, you have to pick something, so the area under the curve is fairly useful. But there's a problem with our collection. Our collection, we have many exemplars, and the performance varies quite markedly across exemplars. So the exemplar we were looking at goes down like this, over like this, and down like that. You'll recognize its shape. But look, we have a quite bad one here on exactly the same topic. It's just a different example. And we have extremely good ones. So tell me, is this an easy topic? Is this a hard topic? Well, first you have to answer, was this an easy set of exemplars or a hard set of exemplars? How would you know what the next exemplar was going to perform at? Well, if you wanted the best error you could possibly make, one thing that you could do is you could take the mean of those curves. Right? So this is the best guess that I can make what the curve for the next exemplar will look like. And if you've given me enough examples, I expect my error from this will be as small as is possible. Right? So I'm going to, the next one might actually be up here, or might be down there, but I won't have a systematic bias. This is the best guess that I could make. So it's this that I compute the area under the curve on, and I say, here's a figure of merit for this topic. Well, not really. That just tells me about this topic. So there's that same number plotted. Right? But now the question is, what about the other topics? Well, you know, this is the same system. A different topic with its set of exemplars averaged, it gets a different result. Is this a 0.35 system or a 0.45 system? Well, it's hard to say from those two samples, but you start to get the idea it might be a 0.33 system. And if you go collect 17 examples, then you could start to see a trend line emerging here, and you could say, well, look, the average precision is around 0.4. Now, we've hidden an awful lot of things here. We switched from interpolated to uninterpolated. We've taken the mean twice now. And so we're really a long way from the concept of precision and recall. And a lot of things are hidden here. And that number 0.4 is a bit of a tricky number because none of them have an average precision of 0.4. Right? For no topic did we get an average precision of 0.4, and yet that's what we'll report as our figure of merit. Now, if we have two systems that we want to compare, we simply do the process twice, and you can see that it got a little better here in system B, got a little worse here, got a little worse there, a little worse there, about the same here, so on and so forth. That one did much better, look at that. And so now which of these two systems is better? Well, you can just do the same trick and compute the mean. It's 0.4. Right? So these two systems are the same. Now, are they really the same? I mean, it might be that one of them is actually 0.399 and the other is 0.368 or 0.3968. So those might be actually different. And you'd like to have some test on the means to determine whether the difference in the means is statistically significant. So we established the null hypothesis that the mean average precision across topics is drawn from the same distribution. If they really were the same system, what's the chance that we observe this difference in the means with this pattern? We do a paired two-tailed t-test. We call the result significant if it's less than 0.05. So that's just a shorthand. You can ask us the number. We ought to have the p-values, but we'll just say it's significant if it's less than 0.05. Your mileage may vary. Now, in this case, system A and system B had a p of 0.094. Well, that says that the difference between system A and system B that was observed could very likely have come from chance. Right? There's only a 6% chance that the distributions were actually different based on the data we had. Now, let's say that it had been statistically significant. So what? Right? The differences are very small. So Karen Spark-Jones has suggested a 5 to 10% relative difference. If it had been 0.5 and it went up to 0.55, an absolute improvement of 0.5, that's a relative improvement of 10%. That might start to be meaningful to a user. So 5 to 10% is the minimum that you'd like to stomp your foot and say, look what we've done. Right? Well, for system A versus system B, the difference is 1/2 of 1% for the ones that I showed you here. So we can't show you all of those graphs for all of these things, but we can tell you these numbers. We can tell you that number, and we can tell you whether or not it's statistically significant for each of the results we'll provide, and we'll provide the number 0.4. So next will be Gina Laveau, who will talk about our first system.
Okay, hopefully I'm audible. I'm going to be talking about translingual and multi-scale query processing. And basically, I'll begin by starting to elaborate that big picture we had of the system processing and start bringing you into a bit more detail about exactly how the processing works. We have, this is a simplified, somewhat abstracted version of our system, but has most of the primary components. If we begin on the bottom, we show the document processing stream, where we begin with a Mandarin audio stream that's provided by the LDC. It's passed to a speech recognition system. In our baseline case, we've been using output from Dragon's Mandarin speech recognizer. That speech stream is then segmented using manually produced story boundaries, and those now separate documents can be passed to an information retrieval system for indexing. In this case, we're using University of Massachusetts' inquiry system, slightly modified to handle Mandarin since it's a 2-byte character encoding. On the query processing side, we take an English exemplar, as has been explained. And in this case, same example, President Bill Clinton and Jiang Zemin. That English exemplar goes through several stages of processing so that it can be matched in the same space as the document. First, we've had named entity tagging performed on all of our queries, in this case by BBN. We performed some term selection and term translation with assistance from a bilingual term list, and then perform query construction so that we can most effectively exploit the most selective terms and greatest information within the document as a query to the IR system. The IR system will then provide a ranked list of documents as output, which in conjunction with the exhaustive relevance assessments that Doug just described, allow us to calculate, using Treck-Eval software from Cornell, the mean uninterpolated average precision so that we have a figure of merit for our system. I'm going to be talking primarily about the query translation component of this system, specifically the bilingual term list, term selection, and term translation processes. And then further detail on subword level handling will follow. So to begin with the bilingual term list, this is where you employ basically a dictionary-based translation process, and therefore our term list provides our primary source of translations. We have, for this purpose, combined two fairly large lexical resources. One is the LDC's English to Chinese bilingual term list. This list was largely culled from resources available on the web and then agglomerated. Our additional resource is the Chinese English Translation Assistance File, also known as CETA, but inverted. Since it's a Chinese English translation device, we needed to reverse the order so that we could go from English to Chinese. This resource was actually manually assembled by a number of linguists from a variety of text sources. So we've got a mix of both originally electronic form and text sources. These actually produce quite a large lexical resource. The total number of English terms that are covered by the lexicon are almost 200,000, corresponding to almost 400,000 translation pairs. Within that collection, it breaks down further into both single word and multi-word units. So we actually have a large number of phrasal or multi-word unit entries, over 81,000 English multi-word phrasal terms corresponding to about 100,000 phrasal translation pairs. Now, you can see at the high level that the terms are about 2 ways ambiguous in general, and that's slightly higher than what's indicated in the phrasal terms. But actually, if you look at specific examples, you often can get a great improvement in the ambiguity that you're forced to deal with by appealing to larger units for interpretation. So if you consider the case of the expression human rights, if you try to translate it word by word and start simply with the word human, that's got 7 translations in our lexicon. The word right, or its stemmed variant, actually corresponds to 30 translations, which pairwise would be extremely ambiguous and hard to deal with. However, if you deal with it at the right unit, at the right level of granularity, as the phrase, it reduces to a single unambiguous translation for human rights of Rentuan. Now that we have this resource for translation, we're dealing, unlike most web-based query systems that people might deal with, we're not dealing with short 1 or 2 or 3 word queries. We're dealing with entire documents. And to deal with those documents, we want to both identify the correct units within the documents to translate, and then which of those we really think are important enough to go through and carry through processing. So we go through a series of processes to pull out those query terms that we think are relevant and appropriate to translate. We begin with tagged named entities provided by BBN's Identifinder, and this system goes through each query and labels all person, organization, numeric, and date expressions for us, pulling out things like the partners of Goldman Sachs and Company as a person or an organization like the United Nations Security Council. And for instance, in the case of the United Nations Security Council, that's something that we would be able to expect to translate appropriately and less ambiguously as a unit. We also appeal to dictionary-based phrases. Since we have this lexical resource of multi-word units that we can see are less ambiguous in many cases than the individual terms, we also, after tagging for named entities, tag for dictionary-based multi-word units that may not have been caught in the named entity tagger. And these include things like, for instance, Wall Street or best interests or human rights. This is a very simple process to gather up these multi-word units, working greedily across the document, finding the longest matching substring in the dictionary, starting from our current point, left to right, across the text. And then we apply a chi-squared filtering process, identifying those terms which are most selective in the document relative to some English background model. This allows us to filter out very common and often extremely ambiguously translated words like function words like of or which wouldn't provide much for translation but could introduce a lot of noise. So now that we've found our units to translate, how do we actually process them? Well, for many of the named entities, we can simply look them up directly in the dictionary. Security Council happens to be in the dictionary as a unit. However, in many cases, since the sources of the named entities and phrases are different, one from an automatically trained system that BBN uses, another based on the dictionary, we may be forced to fall back to the individual word-for-word translation when the entrant, as in the case of First Bank of Siam, is not actually in our lexicon. For numeric expressions, we've had to incorporate some special processing of digits so that we can properly interpret them in context. For instance, we would like to translate 12:30 p.m. as an appropriate temporal expression rather than as something like 1230, the way one might translate 1969. And we use the punctuation as cues to the appropriate translation as well as the tag on the named entity. For the remaining terms, we do dictionary-based lookup, and we look in our term list. If it's not possible to directly match in the term list, we will lematize as necessary. For instance, televised, which does not appear directly in the lexicon, will actually be lemmatized all the way back to the same base form as television to allow translation. It's not as precise, but it allows us to improve our coverage. So, as I've indicated, there's a lot of ambiguity in the dictionary. There are a lot of possible translations one could create, and we would like to present a single translated query that incorporates as much information as is appropriate in order to find the correct translation terms and make matches in the documents. There are a number of ways we could formulate the queries using multiple translations. One possibility we can refer to as unbalanced queries. That simply says, for any term that you are translating, put all of its translations, or some appropriate number of plausible translations, into your formulated query and send that to the information retrieval system. That is a standard baseline approach, but it has the weakness that terms with fewer translations receive essentially less weight in the IR system than terms with many translations. To combat that sort of problem, we applied the two lower approaches. First, building balanced queries, where each term's list of translations forms a pseudo-term, and that pseudo-term's weight is the average of the weights of the component translations. We also, as a contrast, form structured queries. This approach was introduced by Perkala in SIG-IR 1998 and provides some of the best performance for this sort of cross-language ambiguity handling in information retrieval. And this approach recomputes the weight of this pseudo-term that corresponds to the multiple translations of your original source language term from the target languages, from the individual term and document frequency of the translations. So how do all of these strategies actually work out? We've incorporated named entity tagging and phrase-based translation. We've also done some tuning to improve numeral translation. Well, what we find is that if we begin working from left to right with base words, translating only word for word without taking advantage of any larger units in translation, we get a mean average precision in the mid-30s. If we incorporate phrases, and here for phrases we mean both the named entity tagged phrases and the dictionary extracted phrases, we get an improvement to almost 0.4. And that is, in fact, statistically significantly better. Incorporating an additional source of named entities called from the web and the additional numeral processing provides a small assistance, but it's fairly negligible in this case. When we contrast the first set of translation strategies, which all used the structured query approach that has been so successful in the literature, with simply using the balanced approach, we actually find that they're basically comparable. And the subword approach, the balanced approach, has the virtue of extending smoothly to the subword approach that we're going to be following in many of the extensions to this work in the talk. So we've done a lot to improve our coverage and to find the appropriate units to translate, but we still have some gaps in our coverage in translation. In our experimental set, for a total of about 87,000 term instances, corresponding to about 12,000 distinct terms, about 3,000 of the instances were actually out of vocabulary. We were unable to translate them using our strategy up to this point. And that corresponds to just over 1,000 distinct words that were simply nowhere to be found in the dictionary. If one looks, though, at the words, this is frequency ranked of the words that were actually untranslatable for us, we find, actually quite startling, a fairly clear trend. These are all names, things like Suharto, Netanyahu, Star, words that are common in news and also very selective, very useful terms for doing information retrieval, but which can be very topical or change regularly, and which are highly unlikely to be found in a static lexical resource. So for that, we're going to be taking some deeper subword and transliteration strategies that Helen will be discussing.
So, excuse me. So subword transliteration is actually a last-ditch effort to try to make use of the unknown, untranslatable query terms in our query. So the idea is as follows. Let's assume Gina gives me a word like Kosovo, and she says, oh, I can't do anything about it. I've exhausted all my translation resources. I can't make anything out of Kosovo. Now, incidentally, Shinmin and I have sampled newspapers in China, in Taiwan, in Singapore, and in Hong Kong, and we have found that Kosovo gets translated in these Chinese newspapers as 3-character words, and there are a number of variations. And if you look at their pronunciations, they're rather similar to one another. Kosovo, 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 Kosovo. So the idea is, well, if we actually get Mandarin audio coming in, even though we cannot translate Kosovo from our English term from the query, maybe we can try to get at the English pronunciation and try to make up some Chinese sounding pronunciation and try to find it in the audio. And this is the idea behind subword transliteration. So the idea is we have this term in the English query exemplar, and we'd like to be able to transform its pronunciation into some kind of Mandarin pronunciation and try to search for it in the Mandarin audio document. So essentially now we're doing retrieval where we're trying to do a match in phonetic space. So in this project, I've been working with our 3 student members, Wykit, Berlin, and Karen, on a procedure that will allow us to do that. And here is the procedure. So we started with some named entities that Gina passes to our system. And then we said, well, actually, there's a good chance that some of the words are originally derived from Chinese names. So say, for example, I take the names of 2 of our members, Wang Jianqiang and Wang Xinmin. Jianqiang is from Beijing, and Xinmin is from Taiwan. So the way they spell their translated, and this is translated from Chinese to English, their English names is slightly different. Pinyin is adopted for mainland China, and the Weijiao's convention is adopted mainly in Taiwan. And so we developed some procedure that can simply syllabify it and map them to syllables. And these can then be directly used for retrieval, because we're performing, in a moment you'll see we're performing syllable recognition on our audio document collection. Now what happens if we are encountering names that are not Chinese names? Then we basically treat them as English names. I mean, we use English pronunciation rules and apply them to the spelling, such as the name Christopher, for example. So essentially, we're trying to acquire an English pronunciation for this name, and we can do it by one of 2 ways. First of all, we look up a pronunciation lexicon. This is actually LDC's PronLex, and see if that name appeared in the pronunciation lexicon. And if not, then we have developed an automatic spelling to pronunciation generation tool to automatically produce a pronunciation from the spelling. And the background behind this tool is I've used the transformation-based error-driven learning approach, which is a machine learning approach proposed by Eric Brill in 1994. And I've used this approach to learn from PronLex, the letter-to-phoneme mapping, using 85K words for training and 4,500 for testing. And this is the phoneme accuracy and word accuracy. Now, in fact, I believe I don't have to be very precise for this procedure because I have to cross the phonetic space anyways. But in fact, this is the output of my spelling to pronunciation generation system for the word Christopher. So you can see it's a decent English pronunciation that has been generated. So now we have moved from spelling to the English phonetic space, phoneme space, and now we have to find a way to then move to the Chinese phonetic space, which is the syllable space. So here, to continue, we have the English pronunciation for Christopher, and we know that Mandarin Chinese is a syllabic language, it's a monosyllabic language. So for the consonant clusters that appear in English, they will no longer survive in Chinese. And one of the procedures that we did is we wrote a set of phonological rules which we call cross-lingual phonological rules, that inserts the syllable nuclei at the appropriate places, especially at consonant clusters and also at word final consonants. Because word final consonants in English, when they get transliterated into Chinese, often start a new syllable. The situation is similar for Japanese, in fact. So here I have illustrated two of the issues that we try to address in these phonological rules. There are others, and it's a close set. But essentially, when we insert a syllable nuclei, we insert the schwa. So now it becomes karisatafa. Okay? So now we actually are ready to move from the English phonetic space to the Chinese phonetic space. And here we try to perform cross-lingual phonetic mapping from English phones to Chinese phones. And these are phones. Yes?
The first part where you have this Curtis buffer.
This one. This one.
That's adjusting it so it gets closer to the Mandarin.
Yes, it's adjusting it
So
to
it's a
get
kind of adjustment of English
to a monosyllabic.
extra.
Yes, adjustment of English, which is a language with consonant clusters, to a language which is very monosyllabic in nature. So that's an intermediate step that, in fact, eases this subsequent procedure. So in this subsequent procedure, we're trying to map English phones to Chinese phones. And these we call phones, we decompose them from their syllable units. So this is subsyllabic units, what we call phones here. And we're very short of training data in this stage. We again use the technique of transformation-based error-driven learning to learn the mapping from English phones to Chinese phones. We're short of training data. We have a 4,800 word for training. And these are words where we have the English name and its Chinese transliteration in characters. And from that, we derive its pronunciation. And then we try to align the two pronunciations using a finite state transducer. And then the transformation-based error-driven learning method will learn the mapping. Now, this corpus is actually partially donated to us by Professor Chen Shenxi from National Taiwan University. We have also augmented on it by scrounging the web for different names. So now we have mapped the English phonemes into the Chinese phonemes or phones. So here you see ke, li, si, to, fu. Okay, that's the output of our cross-lingual phonetic mapper. But mind you, on the document side, we actually have syllables. So we need to produce syllables from this Chinese phone sequence. And for this, we borrow ideas from speech recognition. We create a Chinese phone lattice by expanding this hypothesis for each Chinese phone, we expand the hypothesis with its likely confusables. So then we create a Chinese phone lattice. And then we trained up a syllable biogram, which is, again, trained from these 4,800 words, to traverse the lattice and search for a syllable sequence. So the idea is similar to lexical access in speech recognition. And lo and behold, here, for a hypothesized syllable sequence, it becomes ji, li, si, te, fu. Okay? Ke and zhe are oftentimes used interchangeably in Chinese transliteration. For example, Lewinsky is transliterated as Lai Wen Shi Ji, where the ski, the K, in the consonant cluster in the last syllable becomes G. So, and we see this effect in our language model here. And here is the actual reference. It's ke, li, si, to, fu. So we probably get some partial syllable bigrams correct in this particular case. But
Excuse me.
yes.
When you say reference, that's really what Christopher. I mean, I suppose
Yes.
that's Warren Christopher, right?
Yeah.
Right. And this is how Warren Christopher is written.
Yes. In
It's
one.
called reference, and the yellow thing is the way your I don't know, machinery was predict.
Yes.
Right.
That's correct. So how will this cross-lingual phonetic matching work? Here we've run 3 sets of experiments. where the green is without cross-lingual phonetic matching, or actually we use this term interchangeably with subword transliteration. So green is without, blue is with, we call it CLPM. Our group likes to refer to it as CLPM. So green is without CLPM, blue is with CLPM. And for this pair of bar charts, indexing term is words. That means we're mainly retrieving on words, but when we encounter a word that we cannot translate, we will augment our word representation with whatever the CLPM produces in terms of subword. Yes? Sorry, I can't hear you.
Did you perform a separate, so this is an evaluation in the context of
Retrieval.
You
Yes.
do an evaluation of the mapping separate.
Yes, we did an evaluation based on a set of 200 words. And the syllable, it will be in our report. I can't remember for the top of my head, but anyway, it will be in our report for that run. So here, for this pair of bars, we're retrieving on the word scale, but when we encounter a word that we cannot translate, we will try to transliterate it and then augment our word representation with that transliterated representation, which is what gives this small amount of gain. And in characters, you see a larger amount of gain and a gain in syllable retrieval, syllable-based retrieval as well. So essentially, we see a small gain with the use of CLPM. We have tried to conduct statistical significance tests on it based on TDT2 corpora. It does not show up to be statistically significant. However, the trend is repeatable. So it's a small gain, and it seems to help. So now we have addressed how we can do multi-scale translation. So at the word scale, we can go from phrases to words, or phrases to named entities to numeric expressions to words, and then down to subwords. So that's what we mean by multi-scale translation. Now, that's actually a facilitator to formulate a query. How can we formulate a multi-scale query? And this is another new aspect of our project. At this point, we have a bag of English query terms, which are selected. Gina mentioned it earlier. Since it's query by example, we have a long query, which consists of the entire newswire. We need to select terms, hopefully the content-carrying terms or the appropriate content-carrying terms. And therefore, we get a bag of English query terms. Now, we need to go through translation, multi-scale translation, to produce a multi-scale query representation in Chinese before we can use the query to retrieve the documents which are in Chinese. Now, what are some of the desirable properties in this so-called multi-scale query representation? Well, it should integrate translated phrases, named entities, numeric expressions, translated terms, and transliterated syllables. It should also be multi-scale, so it should also be at the word scale, character scale, and syllable scale. And for the subwords, I mean the n-grams. So how do we integrate all this together? We designed a sequence of transformations to allow that. And here I will illustrate with an example. So here we have an English bag of terms. Israeli Prime Minister. This has been identified by Gina's system as a phrase in her SATA lexicon. And this is a named entity which is identified by BBN's system, Benjamin Netanyahu. So that's an English bag of terms. And in fact, in a real situation, here it seems like it flows from one term to the next phrase to the next named entity. But when you see a real query, the adjacent terms actually don't mean much in that order because they're essentially a bag of terms. So now, Gina's system can provide a translation for Israeli, 以色列. Prime Minister becomes 首相. In fact, for Benjamin Netanyahu, we can find a translation for Benjamin, from the, so it's, part of it is translatable. But Netanyahu is not translatable, so that goes to my system, which produces a syllable sequence. And here I have, in fact, included the syllable bigrams, overlapping syllable bigrams from the syllable sequence. So I have Netan, Tanya, Yahu. And if we take the query at this point. In fact, what we have now is a query that is based on words. So if we can essentially have a word representation of the query, or for words that we run into trouble with, we can augment the query using syllable diagrams. So it could be a homogeneous query, or it could be a heterogeneous query where we back off to syllable diagrams when we run into trouble. And in fact, we call that a back off. When you hear us mentioning words backing off to syllables, that's what we mean. We can actually take it further. Remember earlier in my example, I said character n-grams can help ameliorate word tokenization problems. So here, we take it further. We generate character bigrams from this 3-character word. 以色列 becomes 以色 and then 色列. And then this has only 1 character bigram. This produces 2 character bigrams. And this is the same sequence of syllable bigrams inherited from upstairs. And if you take the query at this point, now you have another scale of representation. You can probably just look at the query, if you like, in homogeneous form and just look at the character bigrams. Or you can say, well, if my character bigrams run into trouble, I inherit my syllable bigrams from transliteration. Then you have a heterogeneous query. And that we refer to as character bigrams backing off to syllable bigrams. Now finally, you can take it even further. You can look up the pronunciation lexicon for Chinese and map each of these character bigrams into their syllable bigrams. So now what you have is a homogeneous syllable bigram representation of your query. However, a lot of knowledge has trickled down. Well, of course, there's some loss of information because there's loss of information when we go from words to character bigrams because we lose some lexical information. And when we go from here to here, we lose some more lexical information. But at this point, you can see that we're integrating within a homogeneous representation within term overlap, so sequential constraints within a term. So 以色列 becomes this part in the red. And we don't cross terms because the order is meaningless. And Benjamin is 本节简明. And then we have also incorporated transliteration. So we have incorporated within term sequential constraints. In this representation, we have incorporated phrase-based translation, word-based translation, and also transliteration. And if you take the query at this point, you get a homogeneous representation of syllable bigrams. So in fact, you can actually formulate a query from the words only, or characters only, or syllables only, or words with the full syllable bigrams. That's what we will be calling loose coupling. You'll see in a moment. Or characters with the full syllable bigrams, or characters backing off to syllable bigrams, words backing off to syllable bigrams. So this will be a primer for some of the terms that we will be using later on. Now I'll pass to Shinmin to talk about multi-scale document, audio document indexing.
Also, in this previous example, Helen has illustrated why subwords may be helpful in our translingual spoken document retrieval task. However, subwords actually have less lexicon meanings. So what we aim to do is to use both words and subwords. So now, Dragon word recognition output are provided. So what we need is we need to extract character and syllable. So we can extract character using Dragon recognized words, and we can have a character-based indexing. This is just using a tokenized. It's very simple. It uses very simple technique. And then we can have a syllable-based indexing, and the syllable can be derived by pronunciation lookup using Dragon words. However, we also want to address the problem of speech recognition errors. So we want to argument with alternative hypothesis. And as Helen has mentioned, that the syllable recognition error will be the most serious problem, because once your syllables are wrong, then all the approach will be failed. So, and also in our previous experiment on Mandarin spoken document retrieval, we found that syllable lattice will has helped prove our spoken document retrieval performance. So now, given dragon syllables, we want the best idea is to develop a syllable recognizer to produce some alternative syllable candidates, and try to generate a vertically vertically aligned syllable lattice representation for the document. So before doing that, we have evaluated dragon recognition accuracy. And against the anchor script, we found that word accuracy is about 82, while the character accuracy and syllable accuracy is about 88 and 92 respectively. And we also found the syllable substitution errors is about 5%, which means that actually there isn't much room to improve using this architecture. So, we have also evaluated our main syllable recognition accuracy. The acoustic model was trained on half-full Mandarin VOA data. It's about 11 hours. And our syllable accuracy is about 70, which is much worse than compared to dragon syllable accuracy. So to make our main syllable more useful, we have to improve main syllable recognizer. And we also need to design a new structure for document indexing, which can incorporate dragon words, character, and syllable hypothesis, and together with our main syllable hypothesis. And we hope that our syllable hypothesis can be complementary to dragon's syllable. So first of all, we have to improve our acoustic models using speaker adaptation techniques. So we have, for each document, we have VOA audio, and we have dragon speech recognition output. So we can, the speaker adapted acoustic models can be obtained using force alignment and speaker adaptation techniques. And then the baseline acoustic model can be adapted to the speaker adaptive models. So after doing the speaker adaptation, main syllable accuracy can be improved to about 87.8%. So then we also incorporate language models. So in the previous slides, the recognizer didn't use the language model. It's only free-syllable decoding. So after using the language model, syllable trigram model trained from 1998 Xinhua Newswire text corpus, the accuracy is about 90. And this accuracy is actually very close to dragon accuracy, 92. So for audio document indexing, now we have dragon syllable. Actually, this slide I will only talk about syllable level document indexing. So we have dragon syllable, and we have main syllable, and first of all we can think of this. Think of them as a revised syllable lattice. So we can extract overlapping syllable n-grams, and this slide shows an example of overlapping syllable bigram, just using this lattice. And also we can also think of them as two separated recognition output, and we just extract syllable bigram separately. So this slide for syllable level indexing, and for all the multi-scale audio document indexing, we have syllable dragon words, so we can have word indexing, and So from dragon word, we have dragon character. Then we can extract character bigram or character n-gram using dragon character. And then we have dragon syllable. We can also have syllable bigram or syllable n-gram. And we have main syllable. We can using syllable index, main syllable indexing. And we can use all of these sources as separately. So we can have word indexing, character indexing, syllable indexing, and main syllable indexing. We can also combine these together. For example, we can fuse dragon word with main syllable or dragon word with dragon character. And we can also use very tight coupling of dragon syllable and the main syllable. So the next one will be YK to talk about the word subword fusion.
Hello. Hello. Yeah. Okay. Okay. So far, we have told about the indexing at different scales. We have the indexing term using words, indexing using the syllable bigram, using the character bigram. Then you may ask the question: how will we combine together these different indexing terms together to get a better result? There are two major approaches. One is the loose coupling, and the other is the tight coupling. For loose coupling, we mean that we have the word retrieval once individually separately, and also we have the character bigram or character n-gram or the syllable n-gram once separately, and get individual ranked list of results for this different scale of indexing terms. And then we will do a weighted sum using this equation to merge the ranked list of these separate ones to form a filled ranked list for our final evaluation. Say, for example, we are working on K is a set of the indexing term we are using. For example, we use word and character bigram. Then for each of the query and document pair, there will be a score for each individual ones in the ranked list, and we will assign some weight to the different scale of the results. Say, for example, we put more heavy weight on the character and put less weight, say for 0.2 for the word result, and by summing together, we will get a final list of the final ranked list of the coupled result. And this graph shows the result of the loose coupling. The first cluster of these three bars, this is the result for the word retrieval, and this is for the character bigram retrieval, and this gray bar is the result of the loosely coupled word and character bigram. For the coupling between word character bigram, word syllable bigram, and word with the main syllable bigram, that is a consistently certain degree of improvement for this type of units. However, for the character coupling between the character bigram and the coupling between the character bigram and the main syllable bigram, there is actually a slight drop in the results. And for the coupling between the syllable bigram and the main syllable bigram, then there isn't any improvement observed. And yes. The weight is manually assigned. We have do a series of experiments to sweep through the from point 1, point 5, point 9, and then just sweep through these numbers to try to find a best value for it on our development test set. And another way for the coupling is we call it tight coupling. It is a unified indexing of words and subwords n-grams. For example, we have the word Italy, the Prime Minister, and the Benjamin, and the Netanyahu. For this Chinese words in the dictionary, we can use a word-based retrieval. We can use these words as the terms, and for this Netanyahu we could not find in the Chinese word, so we will use a cross-lingual phonetic map to map it to a syllable base, and we'll use the syllable bigram. And in the tight coupling method, we just put this word and this syllable bigram together in the queries as a bag of units in the queries. And for the document, we will combine the Word document and the syllable bigram document together by concatenation. And after that, we will use the resultant query to perform retrieval on the combined document set. And this will give us another rank list for the tight coupling results. In this graph, it shows the comparison between the individual ones and the coupled ones. And it can be seen from the graph that for loose coupling, there is a slight improvement over the character bigram after combining the character bigram and the word. But for tight coupling, there isn't improvement over the character bigram, but only improve compared to the word retrieval, it gives a slightly better result. Okay. And then let's pass to Erica. Okay.
Okay, you've been hearing about our system and everything we've been building for the last 6 weeks or the last 5 weeks. So the question is, just how high can we go with our system? Assuming that we could get perfect retrieval, that would translate into an average precision of about 100%. And that's practically impossible to get if you have a huge number of batches, huge number of topics, as Doug was demonstrating earlier. If we got 100% average precision, that would mean that every single relevant document had been retrieved in order at the very beginning of our ranked list. So for example, if there were 10 relevant documents, the first 10 documents we got were all those relevant documents. Now, why can't we get perfect retrieval? And the reason is because whenever we're doing retrieval, we get corruption in our data sets. And we'll talk about some places where noise gets added. First, we start with our English Newswire article. When we take this article and we transform it into some fashion that the retrieval engine can understand, we have problems with term selection. As Gina mentioned earlier, you're getting terms that may not be very useful, generic terms like one. Additionally, you're going to get translation errors, just wrong translations because of the lexicon or wrong translations in the context. That is also related to translation ambiguity. If you get the word bank, you don't know what type of bank you're talking about, whether it's a financial institution or whether it's something like a riverbank. And finally, there's the problem of out of vocabulary, which we've spent a lot of time discussing, words that your dictionary just doesn't know. On the document processing side, we have several places where ambiguity occurs, specifically with our Mandarin audio files. First of all, if the speech recognizer fails, we get speech recognition errors. We have a problem with word tokenization ambiguity, especially with Mandarin. You have a sequence of phonemes. Where do they divide into words? And where do they divide into syllables? And then, as always, out of vocabulary is a problem. If the words are not in the language model for that syllable recognition, we're just not going to be able to produce them in the output. And finally, we have the fundamental problem that on the English side, we're dealing with New York Times or Associated Press, which have their own styles and their own vocabularies. And on the Mandarin side, we have Voice of America, which has its own style. And how can you overcome those differences in news styles? So because of all these additions of noise, this corruption, we are going to be unable to get 100%. So we decided to find out just how high we could go. And we had 3 different sets of experiments. The first was to take the Mandarin Voice of America experiment and run it against itself. This is basically a cheating experiment, but it was just to establish an upper bound. We tried matching it directly against itself, which means against ASR output, and we got about 73% retrieval, average precision. And then we tried matching it against anchor scripts. The anchor scripts were what the anchor sat and read in front of the microphone. So presumably, we're avoiding the issue of speech recognition errors. And we got only a little bit better, 73.8%, or 0.738, something like that. Then we stepped back and said, okay, what if we use different sources, but still in monolingual space? So we took Xinhua, which is Chinese newswire text, and tried to retrieve Voice of America documents against Xinhua text. This brought back that source difference problem I mentioned. And because Chinese is written without spaces, we had to tokenize the Xinhua text into words in order to do this retrieval. Dragon was already tokenized, and that created another problem. Using that experiment, we got around 53% against the Dragon scripts and 58% against the anchor scripts. So,
This is against Xinhua against Xinhua.
no, this is Xinhua against Voice of America.
Voice of America in Chinese.
Right, and Xinhua in Chinese. Yeah, so we're staying in Chinese space, but between different news sources. And then our third experiment was to take...
Excuse me, sorry. And the Voice of America was Chinese Voice of America?
Yes.
I see, so we're
Right,
always in China.
in those 2 experiments. But then we decided to move into translingual. So we started with a New York Times article, but to avoid translation problems, we got a perfect translation. Well, our so-called perfect translation. And we took that and ran it against Xinhua, or ran it against Voice of America transcripts again. And our best result there was around 50 to 53%. So in other words, it looks like about the best we could do on word-based retrieval was somewhere between 55 and 60. That would be our upper bound on how well we could do in words if we could achieve perfect translation and to some extent recognition. Yes? I'm sorry, ASR output did better than New York Times? No, at this point.
Although it looks like a big difference between topic variations is large, some go up, some go down, so that the statistical significance is quite low. But on the other hand, we don't have an answer.
A possible answer is tokenization problem. Because we don't have Dragon's language model. Dragon's language model causes the recognizer to produce a sequence of words. Right? So if you give me a sequence of Chinese characters and I don't have Dragon's language model, actually we have our own tokenization. So I will also given the same sequence of words underlying me, Dragon will produce a sequence of words from the same character string. I will try my best to produce a sequence of words, but they may not match. Yeah, that's a possible reason.
Yeah.
Did you do the same experiment on English to English, or can you use key results to also look at the language differences?
No, we didn't.
Yeah, but that's a good.
But if you change collections, you'd expect all the numbers to change. So a lot of things would be moving at the same time.
And then finally, because we've been discussing the issue of character bigrams and syllable bigrams, we ran the same experiments using Xinhua and the perfect translations in character space and in syllable space against the Voice of America again. And as you can see from these, let's see, gray is words, green is characters, and blue is syllables. Character bigrams perform marginally better than the other two types of indexing terms. Syllable bigrams are similar to words, but slightly worse. The differences aren't statistically significant. And overall, we're still abutting against that 0.6 mark. So if we could ever get close to 0.6 with our retrieval system that we've spent this time building, we figure we're doing really well. And as those are our targets, I'll pass it on to Sanjeev to talk about what we actually achieved.
Okay, now it's time to dazzle you with numbers. So what happens is in these systems there are many, many parameters, and what we did is when Gina presented her results and Helen and YKit, we had controls, as in when Gina did something, she had 200 terms selected for translations, she made so many translations, did the structured queries and so on, and within her results everything was sort of consistent. And so if you wanted to see what phrases do for you, or in Helen's case, if you wanted to see what the cross-lingual phonetic matching does for you, those numbers are all believable as subsets. But then we said, okay, let's imagine we're going to play this game of competition and we're going to actually try and build the best system. What can we do? And so here are all the numbers. I mean, they look like bars, but they're really numbers. And what I'll do is, for those of you who've been paying attention, you know exactly what each of these means. But for those of you who don't, and how many of you don't, I'll just step you through them. Okay, so here, first, these two are sort of Gina's systems, as in, like, and by the way, these are everybody's systems. Pat wrote programs after programs so that by throwing a switch here and changing an option there, you can run any one of these systems. And Erica has run about 5,000 such numbers, and these are the best of them. So you're seeing a very, very concise summary. So these two are things that Gina talked about. So you're doing phrase-based translation. You can translate you can translate a few numbers, a few named entities, and you're doing balanced translation as opposed to structured queries. It turns out balanced translation is the one that works best for us. So if you do that, then in a fully word-based environment, we get a average precision, a mean uninterpolated average precision about 0.46 or something like that. So that's the best a word-based system does. Now, a character-based system beats it fairly significantly. It's about 0.51, I think, 0.514 or something like that. And this is a statistically significant difference. So we expect this difference to reproduce itself when we go to another test set. So that's one. Then these three numbers over here, they correspond to what you get by adding the cross-lingual phonetic matching for proper names which are not in your translation dictionary and your meager named entity list. So again, it turns out that if you put them, remember now Helen had this multi-scale indexing chart or multi-scale query formulation chart. So this is the one where you had words along with the syllable stuff. This is where you had character bigrams and syllables. And this was at the bottom of her chart, the all-syllable system. Now we optimized everything else for it, as in we use the balanced translation, we use the full queries as opposed to 50 terms or whatever it is. And when everything is done, these are the numbers you get. So again, over here you can see that the character-based system performs best. And all these systems, between this word-based system and this word-based system, there is a small and statistically not significant difference. And between this character-based system and this character-based system, there's a small and statistically not significant difference. But this is slightly better. And as Helen said, adding the cross-lingual phonetic matching gives a steady improvement. Maybe we don't have enough topics in TDT2 to claim statistical significance, but we hope it will repeat if we have a larger set.
So the difference between those two is one is purely characters, the other is multi-scale characters plus syllables.
This one?
Yeah.
Yes, so this is a character system to which you have added syllables only for proper names. And this is a character-only system where the proper names just fell to the floor. Okay, so these are two sets of numbers. Now the third set of numbers are the coupled systems. So YKit talked about loose coupling and tight coupling. So this is the best of the tightly coupled systems. I'm sure you remember his chart and remember that the word plus character bigram was the best of the coupled systems. So this is the word plus character bigram system.
loosely coupled, and that performance is 0.53, or 522, I think. And then another thing which he didn't show you is that if you do tight coupling of character unigrams, bigrams, trigrams, then that is actually slightly better than the character bigram system. And so we ran that again with everything else optimized. And finally, we ran these two, the May syllable system and the lattice-based system, which is you form the lattice like Shin-Min was explaining. And so that way you have a document representation which has multiple syllable hypotheses instead of just the one best output. And so we had these numbers. So this is basically the whole slew of results, everything else optimized. And these numbers are all mutually comparable, as in any trait that is not shown here is constant for these systems. And so it's clear that we expect a lot from our character-based systems and from our character plus word, coupled system. We actually expect this system to perform fairly well. So we expect this, this, and this to do well. So if I were going to compete in an evaluation, I would go with one of these systems. So what did we actually do? We did run an evaluation. In fact, Pat tells me the computer is still chugging as we speak, and we have some results, though not all. So some of them are consistent. Here we had a little bit of a surprise, but there should be an asterisk on this result. I know why. There is an asterisk on this version, not on that one. Okay. So the thing is, this system has one parameter misconfigured. So I would expect this number to go up here and match this one. Most of the trends are consistent. The only thing to notice is that TDT3 for some reason seems to have slightly worse overall performance than TDT2.
I'm sorry, I lost. What's the difference between this slide and the previous one?
Okay, you mean this one. This is, I'm just adding numbers to this slide, as in the green bars stay frozen, the blue bars show up to give them company.
Oh, I see.
Yeah. And so, okay, there is a point though. The point is that on the green bars, you're seeing the best of. We tried 50 translation terms, we tried 200 translation terms, we tried all translation terms, we tried balanced queries, we tried structured queries, we tried unbalanced queries, we tried with CLPM, without CLPM, with that, without that, everything. And this was the best. And on this one, we have no idea what the others would have done. This is an honest test.
And the reason TDT2 does better than the TDT3 is because TDT3 is, I don't know,
at this point,
considered more difficult.
Given what we have told you so far, we wouldn't know. We could always admit the possibility of overtraining. But Doug, is TDT3 slightly harder? Okay, so in my right, so one could always claim that we were overtraining, right? So I don't know, but my feeling is it's a difference between the collection that could explain.
It's a relative difference that counts. Within TDT3, if one of them is better, and the same pattern is present on TDT2, then it's a better system.
So if the choice was of these, which system would I go with? I'd probably go with either the words plus character bigram coupled system or the character system with the cross-lingual phonetic mapping, and they do end up doing the best even in the blind evaluation.
Are the corpus sizes the same?
No. The TDT3 is a much bigger corpus. It has 50-something topics as opposed to just 17. And the density of topic, whatever, the density of documents and topics is a bit different and so on. Yeah, and the database itself is about 50% bigger.
But the average precision is computed over the same number of
Okay. Okay, so the dark blue averages are, first of all, a larger number of topics at the highest level. We have 56 topics as opposed to 17. But inside that, remember we talked about multiple exemplars from a topic. That's the same. This was done over 12 odd exemplars. This was done over 12. There are a few topics which don't have 12 exemplars. They have only 5, so we did 5. And the same holds for the green and blue bars. Yeah. Over here you do have multi-scale, because remember the transliteration takes you only to syllables. So if you had a word-based system, you would need syllable indexing to go hand in hand. And if you had a character-based system, you'd still need the syllable-based indexing to go. So this one, this one, this one, this one, and the lattice. So all of these are multi-scale systems. This is a syllable bigram system with our syllable output rather than Dragon's. And the reason why we had it up here is actually, maybe I should go back and explain. The thing is, we wanted to have something to compare the lattice-based system with. As in, like, when you have two alternate hypotheses and you construct these crisscross bigrams and index the document with that, how do we do? And since one of them came from Dragon's output and the other one came from our recognizer, we thought that we would compare this to the May syllable system and the original syllable system. The idea being that the lattice is in some sense a tight coupling of the May syllable system and the Dragon syllable system. So that's why we had it up there. But since it didn't do all that well compared to these guys, we put it on the back burner when it comes to TDT3, and those are going to run tomorrow. This one I think is running right now, and we might have that by the second session actually. Yeah.
One question about the normalization for the combining of your final results. Is anything done to address the fact that you do have various number of exemplars and true relevant hits? So if you have two exemplars, you might just be in a bad case, or overly optimistic. Is there some kind of weighting done on the relative sizes of number of exemplars and the number of on-topic possible results?
No. What we do is we treat all topics the same, as in if this topic happens to have few, that's it. As for exemplars, we try to go to 12 if we can, as in if a topic had 12 exemplars or more, we would choose 12. There are a few topics in both the green and the blue which didn't have 12. For those, we took just all that we had. But these are by the way the English exemplars. We don't know. I'm not referring to how many Chinese audio there were.
How do you use those small documents? Choosing randomly to introduce some other variation?
In fact, it introduces a lot of variation, as Doug showed in his first slides. The curves were all over the place, and they were chosen randomly. Once, as in. So for instance, no, we didn't do multiple runs, no. So we chose 12 exemplars. So from the slew of New York Times AP Wire stories, we picked 12, and those were it. Sorry? Their recognition performance in broadcast news? Does anyone know? I don't, maybe Bill might, or. Okay. Oh, I thought you were asking how they did in the Hub 4 task.
She asked whether it was trained on broadcast.
Oh, whether it was trained. The answer is we don't know, but I would believe yes. Meaning this is the standard. What comes from the TDT2, 3 collection is just their output, but I would believe it is trained on maybe more than just broadcast news. As in, they were not restricted to anything. They were just told, give us your best system. Charles, do you know? Okay, so that's the right. So I suppose the answer is yes. Okay, Doug, should I take it? So.
We've got a question period after this, right?
Okay, actually, maybe I should let Helen conclude, and Helen has some nice conclusions to go after this, so we can. Oh, absolutely. Otherwise, you'll hear all the stuff I say to Doug.
So to summarize, in this project, we have proposed a novel multi-scale paradigm for cross-lingual spoken document retrieval. And this approach aims to ameliorate the translation OOV problem and the recognition OOV problem. And within this paradigm, we have to devise methods for multi-scale query and document processing. And under this, we have some new ideas, such as in the development of CLPM to be able to do transliteration of subwords when we cannot translate, and how to couple them in the query and document so that we can have query and documents in multiple scales. They embed words, characters, and syllables. And in fact, a point that deserves to be a bullet here is that the popular approach for cross-lingual IR is on a word base, on a word scale. And if we introduce the subword scale, then what does that mean by translating subwords? And that's where we do transliteration. Translating subwords is what we refer to as CLPM, transliteration. But actually there's a host of issues that come after this, which is when you do cross-lingual IR using these translated subwords or using these subword units, then there's a host of issues that have to do with weighing the query appropriately and using that to retrieve the document, which in turn have to be weighed appropriately because we're now using subwords. And then we also looked at the problem of multi-scale retrieval, and by that we mean various tight and loose coupling strategies to fuse words and subwords for retrieval. And from our extensive experiments on TDT2 and TDT3 corpora, we have found that character biograms typically outperform words or syllable biograms in retrieval. So it seems to be, this is supporting evidence as to why subwords may be useful, especially for our task. And also, the fusion of word and subword units show potential in multi-scale retrieval. We have seen that in loose coupling, it gives us some degree of gain. In tight coupling, it did not, but it probably merits further investigation. And also, we have tried the idea of using different recognizers, different recognition outputs to index the audio and try to combine them in various ways, one of which is using a syllable lattice, so that we have this document representation which is compounded by technologies from two recognizers and use that for retrieval. Now, this we have found in the May project to be not very helpful in terms of retrieval performance. However, previously, work done by Shinmin and Berlin have shown that in monolingual spoken document retrieval, having the syllable lattice is actually very helpful because it gives you alternate hypothesis in terms of the syllables, which brings about robustness in against speech recognition errors. There are a lot of future directions that one can go forward from this project, and here I'm only listing a few of them. I'm sure if you talk to various members in our team, they will give you their views as well. First of all, we feel that word-subword fusion techniques merit further investigation. We think that there's a certain degree of similarity between tight and loose coupling, and the discrepancy we see in retrieval performance now is probably due to ourselves not having enough time to understand the problem more thoroughly. We're also looking at the possibility of multi-scale query expansion for retrieval performance improvement. In monolingual spoken document retrieval, people have shown that query expansion is helpful towards retrieval performance. Now we take it to the multi-scale level. How do we do multi-scale query expansion? And this is Wai-Kit's proposal for his continuing thesis research at Chinese University of Hong Kong, and he will speak briefly about it after the break. And then furthermore, another idea is so far in our retrieval of spoken documents, we have not incorporated acoustic scores that we get from our recognizer. And we believe that especially because we're using subwords, we're introducing a lot of subword n-grams into the representation, which means that weighing them appropriately will become a very important, well, actually is a very important issue. And we have only scratched the surface on that. And one possibility of furthering that step is to perhaps incorporate acoustic confidence scores into the retrieval framework. So that's what I'm going to say for as far as the May project is concerned. But before we close, I'd like to first thank all of you for your interest in our project. Also the sponsors for their support. I see our sponsors in the audience. And especially to Fred and his staff for running the workshop so well for us. And last but not least, my team for all the hard work, and we have a lot of fun, and to me it's an extremely intellectually stimulating summer, so I thank my team especially for that. So that ends our presentation.
So we'll have a break. I noticed that we have a rather large lunch break, so we can afford to run a little bit over time. So it's now a little late. It's about 11 o'clock. So let's come back at 11:20, and then we're going to have Wai-Kit talking and a general discussion of this presentation.
So I believe in the next 45 minutes or so, we will be spending 15 minutes on Wai-Kit-Low's proposal, what he's plans to do as an extension of the May project, and the remaining 30 minutes would be question and answer. So a short introduction for Wai-Kit-Low. He is a PhD candidate in the Chinese University of Hong Kong. He has been working with me for about a year, and this summer he has come and joined our group, and he has been involved in various aspects in the May project, including the CLPM part, and especially he's the instrumental person in looking into the problem of loose coupling for word-subword fusion. So now he's going to present to you his idea of how he would like to extend on the May project. So Wai-Kit-Low.
Welcome everybody. The proposed continuation work for the May project is on the multi-scale query expansion for cross-lingual spoken document retrieval. First of all, I will give a brief review on the main aspect of the May project, and then I will present the research goal of this proposed continuation work, and I will then elaborate the multi-scale query expansion. This includes the word scale expansion and also the sub-word scale expansion. And finally, I will give a summary of the work. During this summer, the May team has been working on the multi-scale query and document expansion for the cross-lingual spoken document retrieval task. And we have quite a large amount of good resources, which include the TDT2 and TDT3 corpus for our retrieval work. And for the May project, it is, as mentioned previously in the presentation, in the previous session, it is a spoken document retrieval task using English text query, which is query by example to retrieve Mandarin Chinese spoken documents. For the multi-scale representation, there are several advantages. First of all, on the word scale, it provides the lexical knowledge which is known to be quite useful for the retrieval task. On the sub-word scale, it can circumvent two major problems. One is that when there is a translation out of vocabulary problem in the query, we can always back off to the transliteration at the sub-word scale. And on the other hand, in the document size, the audio indexing process may have recognition out of vocabulary problems. And in this case, we can back off to indexing the document using the sub-word units. And as a continuation, in the May project, we use the query by example, which is usually quite a long passage of text material to retrieve relevant material on the related topics. And in most practical cases, the queries are often short lists of keywords. And in this situation, the retrieval will become more vulnerable to the translation error in the queries, and also where if there is some recognition error in the spoken document indexing process, the retrieval process will be harmed a lot. And the goal of this proposal is to try to investigate the query expansion techniques for the performance improvements in cross-lingual spoken document retrieval. For multi-scale query expansion, this includes the two major scales, the word scale and the sub-word scale. On the word scale, we can use some side corpus either in the source language, that is the language of the query, or in the target language, that is the language of the collection, to do some kinds of expansion. And this could be done in an attempt to try to circumvent some of the translation out of vocabulary problem. On the other aspect, we can also use expansion by confusable words. This is to try to provide more robustness towards ASR errors. On the sub-word scale, it is also for providing robustness towards ASR errors. We can do some expansion on the sub-word scale, confusable sub-word, to improve the coverage in the index documents. For word scale query expansion using side corpus, the work proposed is some certain kind of pseudo-validation feedback. That is, we provide a query to retrieve for retrieving of some documents, and we can use a side corpus to do an additional retrieval to get a ranked list of the relevant documents, and then from the top ranked document we can pick out some relevant terms to include, further expand the query before we really do a real retrieval task on our targeted document collection. For the side corpus in the source language, we can expand the query terms set before the query translation. This is aimed to add more related terms and synonyms to for the translation, so as to circumvent some of the translation OOV problem. And this work is inspired by the document expansion work by Sing Hao, which has been an invited speaker in this workshop. On the other side, we can do some query expansion on the target language. This is in this way, we will do the query expansion on the query after the query translation process. This is aimed to include more related terms and synonyms in the target language after the translation. On another aspect, we also propose to use query expansion using confusable words. This is aimed at to achieve more robustness in the cross-media retrieval task. We can identify as acoustically confusable words from the recognizers, the output, and also identify phonetically confusable words using some pronunciation dictionary, so that we can know you can have a word pair list of commonly confusable words from the acoustical and from the phonetical point of view. For example, the English word, English example, you walk, is quite confusable to a walk, and another example in the Chinese is 保护 and 抛溃 is also a possible pair of confusable words. Having identified these confusable words, we can do expansion on the words in the query term to try to recover some of the possible recognition error during the audio indexing process. On the sub-word scale query expansion using confusable words, it is also aimed at to achieve more robustness in cross-media retrieval. We will first try to create a sub-word confusion matrix from the speech recognizer's output, and then we will expand the sub-words in the query term to the confusable counterparts. this will, in our previous experience, we have performed a similar query expansion using computable software, which is suitable in a monolingual Chinese spoken document retrieval task, and there is some observable improvement after using this technique. After that, we have expanded the queries on a different scale and using different methods. We will have the same problem: how could we combine these results, combine these terms together to improve our retrieval. And for the loose coupling method, we can again merge the rank list from the individual ones to, and then to rerank the score of the individual ones to obtain a final rank list for the retrieval. And on the tight coupling method, we can apply both the word scale and the sub-word scale expansion technique to the query, and putting all these expanded elements together in the query before we perform the retrieval. We will try to investigate the relative contribution of the different query expansion strategies towards the retrieval task. In summary, we have proposed multi-scale query expansion for cross-lingual spoken document retrieval task. On the word scale expansion, we propose to use the cyclopedia expansion in both the source and target languages, and also using confusable words for the word confusion expansion. For the sub-word scale, we will try to use the confusable sub-words in the recognition output to try to improve the audio indexing process, and we will have a look into the integration of the different query expansion strategies. Okay, thank you. And this is the end of my presentation of the proposal. Thank you. Is there any questions from the audience? Thank you.
So that concludes the graduate student proposal portion of this session, and I suppose in the remaining time, the May team can address any questions you may have regarding our project. I'll try to hook up my laptop in the meantime.
Okay, so the question is, what did we try that we thought would be really good that, how did you say it? Bomb. Comment?
Well, one of the things we had is every single error we had was either catastrophic failure or actually improved our system. We actually had to go through and clean out some errors, and cleaning out our errors, our system got worse. So it's sort of like you might want to leave it in there. But one of the things we did is stop wording at the beginning of when we first started. Stop wording helped when our system was not very, it was sort of when it was a naive system, stop wording helped. But as things got more improved, the stop wording became less and less of an effect. That's one of the things I think.
Anyone else?
I have this feeling that you had more hope in syllabic, using syllables as units than the results seem to support. And I don't know what the actual results are in monolingual. I think the reason you went into it is because in monolingual syllable-based retrieval seems to be quite effective.
That's correct.
And how effective is it in monolingual compared to, I don't know, word or character-based retrieval?
In our work, well, there are two groups in this team that have previous experience with Chinese monolingual spoken document retrieval. In our work, we have found, and by the way, our task is actually on video retrieval, but we don't use the video frames, we only use the audio tracks. And again, it's a cross-media retrieval task. We have found that using syllable bigrams outperform words. And if we can get near perfect recognition, then it definitely outperforms words. Because we're dealing with real media data, which is very noisy data, we were using, for our task, we were using this other measure called average inverse rank, because it's actually a known item retrieval task. Going from a clean environment, recording room speech, to news broadcast that's distributed over the web, our recognizer's performance dropped from 70% to 30% syllable accuracy. And the corresponding drop is from 0.8, was it? In average inverse rank, that means the inverse of the rank where you found the relevant document. So if it's on the top, then it's 1. If it's way below, it becomes 0. So it drops from 0.8 to actually only about 0.5, high 0.4s. So even with a very noisy syllable recognition output, we were able to maintain a certain degree of retrieval performance in our task. So we had higher hopes for syllable.
Well, is the problem then because the translation makes the syllables so vague? I mean,
yeah, one of the key problems that we have found is because we're doing term-by-term translation, so we already lose all the crossword constraints, which in an overlapping syllable context is something that a sequential constraint that you rely heavily on when you're out of lexical knowledge. And when we're doing cross-language in this particular case, that's a big hit. We take a big hit right there. Yeah.
I'll make one other point on the syllable issue. I think I can live without it. Can I live without that, Mike? Yeah. So this is how you do if you can only do syllables, or maybe even this is how you do, right? But if you can't do syllables at all, you're down here, right? If you can't do words, you're already down at syllables. Well, that's not so bad, right? I mean, this is way up from 0. So in Chinese, where there's a word recognizer, this is great. You can use words. What do you do with Hakka? What do you do with something where you're not ready yet to make a word recognizer? Well, you can get quite a ways with syllables, and we can see how far.
The other comment I had was that on the syllable-based systems versus word-based, this might be due to the fact that we have very long queries. If you had a 3-word query and one of them was not in your recognizer's lexicon, the syllable-based systems gives you much more than a word-based system can give you, whereas if you had 200 words of which 5 were not in your recognizer's lexicon, maybe we don't see as much of a difference because of that. And this is just speculation. I don't have a concrete number to back it up.
Actually, in our group in Academia Sinica Taipei or National Taiwan University Taipei, we have done some experiment on text-based retrieval. So it's a text query to Mandarin Chinese text document. So we have some colleagues in our group has done some experiments on comparing the syllable-based and the character-based, and usually even both the document size and the query size are text. Then using syllable approach give very comparable performance compared to text-based retrieval. And we have also done some speech query to retrieve text document. And in that case, syllable-based sometimes is better than character-based approach. this is because some foreign name and usually will be translated to English to different character sequence, but they always with very similar syllable. So if you use the syllable approach, then sometimes it will be better than character. Even their information is much rough compared to character. And we have also done some experiment on spoken document retrieval. So the document is spoken Mandarin broadcast news, and query is a very short query. It's like keyword-like query. So each query on average is about 3 to 4 characters. So the syllable approach is performance of syllable approach is very similar to character approach, but the word-based approach is very bad. This maybe one of the major reasons is the recognizer is not very good. So the syllable accuracy is about 70 to 80, just like the result we report in this presentation. And I'd like to mention about syllable lattice, because in our experiment, as I have mentioned, our syllable recognition, the accuracy is about 70 to 80. So we have actually we have much room to improve using a syllable lattice to improve the inclusion rate. So so we have many works on syllable lattice representation of both spoken document and spoken query. So the lattice always win in our experiments. And but in this experiment, because we use the inquiry system, so it's very difficult to incorporate the acoustic competence score in the document representation. So I think this is a major reason we failed in this experiment. But I still think the syllable lattice is has very good potential, because sometimes we can have a very good recognizer. For example, in a very noisy environment, or maybe it's a meeting notes retrieval task, then the syllable approach may still give us a very good retrieval performance.
My question is that since your task is really cross-lingual retrieval, so you need to translate words to words. So that sounds like it would make no sense to have a word recognizer combined with word translation, because your syllable would do well in monolingual because you have matched syllables. But when in translation, the syllables don't match to anything in the English space. In that case, I would assume that you do need a word recognizer. And since if you have a word recognizer and with the language model, your recognition accuracy will be higher than syllable accuracy, then your translation would also be better. As what you mentioned that syllable recognition is syllable-based retrieval is higher than character-based retrieval, I also think that makes sense because of the reason you mentioned. But that's for monolingual retrieval. Again, it's identical syllable. You retrieve things that you have in the query. But when you're doing translation, you really need to go from term to term or word to word. And if you use syllable recognition in the front end, then you lose a lot of information that you could, the word recognizer could help you with translation.
Okay, so there are several things to say in response. One of them is that actually, if you'll recall our results, which we don't have up right now, the best results were not on words. They were on character bigrams. And so certainly we needed the words to get to the character bigrams. Right, so we recognized words, and then we formed character bigrams within Word, and we translated words, and we formed character bigrams within Word, and then we matched. And that produced a, I'm sorry? We translate, well, the queries were English, and they were what was translated. So we're translating from English to Chinese and matching in Chinese space. And so because we did not have good tokenization to the word level in Chinese, perhaps, or because the correct level of tokenization in Chinese is ambiguous, whether you'd want to tokenize at a very specific level, long string, or at a more general level, combinations of shorter strings, the bigrams capture all of that in a way that we weren't able to capture with words. So this isn't directly responsive to your original question, but we were getting things from working with subword units, in this case characters, after translation, that we were not able to get at the word level because of tokenization issues, at least in part. That's one point.
What do you mean by tokenization issues? If you have a word recognized, it's token about to recognize.
Okay, Gina, you want to?
Basically, I'm not sure I need it either. The basic problem that we're dealing with is that our lexicon that is a source of Chinese terms in translation does not have an identical tokenization size necessarily to the output of the word-based recognizer. They did not come from the same source. So there's a misalignment that...
What's the percentage of that? Because there are always words, recognition lexicon is always a subset of translation lexicon. They don't misalign.
That's actually not strictly true for our case. Because the lexicon, because of the way the translation lexicon was developed from a variety of sources, it's largely content-wise, it is largely a superset of what's available within the recognition vocabulary, but not entirely. The most common example of misalignment that we encountered, quite trivially, is the particle the modifier particle, which is attached about 50% of the time in things that would be adjectival in the lexicon, but appears attached only about 7 instances in the actual Dragon output. But that would cause a word level mismatch, even though it's trivial from the point of view of semantics.
You cannot have cross tokenization. It will only be a substring.
It might well be a substring. Exactly, it is largely a substring relationship, and that's why overlap only within words for character bigrams is so successful, because it avoids these boundary conditions where the constraint fails. Does that help at all?
No.
Can I ask here a little bit, maybe this will clarify, not for her, but for me.
Sure.
The tokenization problem in the Chinese output, I mean the output of the Dragon recognizer. I don't know why there is a problem, because the recognizer itself thinks in terms of words,
right.
Doesn't it?
Yeah.
And
yes,
therefore,
it is. And
it's not a matter of deciding that the word goes from this character
right.
to the...
It's got a set of words, and the problem, so there's essentially, one of the things we could do to guarantee that we remained entirely within the recognizer space would be to deliberately exclude any element, any translation term that is not in the recognizer's vocabulary.
Right.
That decreases our ability to cover words in the process of translation. So what we are settling for is a partial match in those cases.
Can I try to put it another way? I'll give you an example. Dragon produces the wrong tokenization. There's no question about that. Because the Dragon recognizer produces the wrong... I'm about to give an example. So, please. So Dragon will produce something, if Dragon were working in English, it would, and if it came across White House, it would either give White House, or it would give white and house, but it would not give both. Dragon generates a single tokenization. However, for retrieval, it's actually better to index White House and White House. So we have to get all three of them from someplace. Now, if Dragon over segments and gives White and House, we could put them back together. If Dragon under segments and gives White House, we could split them apart if we knew enough about exactly where we should split them to index them. We don't. If we use what Dragon gives us directly, then we get about 40% mean average precision. If we subsegment into bigrams, Dragon often gives us 2-character words. So we don't do anything there. We just keep what we have. When they give us 1-character word, we drop them on the floor. When they give us 3-character words, we have these 2 and these 2 bigrams. And then we look at what is the mean average precision when we do this. And we get 50%. Now that's a 25% relative improvement, which...
It sounds like it's just theologically not. And also, Dragon will never give White House separately in Chinese, because White House separately will not give you the characters.
I don't know Chinese, I'm sorry. But there are cases where Dragon gives 4-character words that you should subsegment.
What do you mean by should?
I mean, your retrieval performance goes up if you do.
So if your
So the
retrieval
criterion function is only retrieval here. It's not some arbitrary view of correct and incorrect. It's only what improves retrieval.
Okay, but then you can go back from word recognition to your by character, rather than go from syllable recognition.
I haven't said anything about syllables. I was not completely responsive to your question. I started out by talking about subword units and saying that there is in fact a gain from using subword units because n-grams capture both the context and the parts. Now, when we
80% of Chinese words are 5-character words. That's why you're getting most of it probably. But there are a lot of 4-character words which are supposed to be words that maybe your translation lexicon does not have them. That's why you're not capturing them anyway. But I still don't think that's the correct way of doing it. That's my point.
Okay, but we're not actually debating the correct way of doing it. We're debating whether or not when we did it this way or that way, it got better. And we have results to show that. Now, there might be something else we should do, and maybe we should take offline some suggestions for other ways in which we could improve this.
I guess the point I'd like to add is we all know that for Chinese, given a sequence of characters, there are almost all the time multiple ways of tokenizing it. And if in the case of TTT corpora, Dragon provides us with one tokenization, then it may not be the one that we want. It may be in some of the cases, but there are definitely cases where it may not be the one that we want when we have to cross the language boundary. So, was there Chalapati?
Yeah, I actually was a little puzzled with what the differences between the very last lattice, syllable lattice, and the may syllable. So, and let me see if I understood the differences in the experiment. In one case, you have the syllables with the word boundary information. In the other case, the syllable lattice loses the lexical boundary information, or it still has it. Why is it so bad? The syllable lattice, because your claim was in the monolingual case, syllable lattice actually does better. So why is that?
As I mentioned, there are several issues. First one is in this experiment we use a very long query, and we use query translation. So each query English term can be translated to multiple, and can be up to 50. So on the query side, we have many ambiguities, and also on the document side, when we use syllable lattice here, as I have mentioned earlier, the acoustic recognition score cannot be used in this task. So if we use two candidates, you can think about if we have two candidates in each syllable, and we have four bigrams, and if we use 3 syllables, and we will have 9 bigrams. and even one is correct and the other 8 is wrong. So if we cannot use a acoustic comfort score to prune in some to remain some more possible background and delete some with some background with low probability, then the retrieval performance will get very bad. Actually, in our previous monolingual Mandarin spoken document retrieval experiment, if we use a syllable lattice but without a confidence score, then the performance will not be good. It's usually it's worse than only use one best syllable sequence.
So in this experiment, basically you're saying you don't use any kind of ordering of the paths of the lattice based on acoustic score.
Yeah.
Every path is equal.
Yeah. And also another issue is query. It's use a long query and a short query. And if you use a short query, then lattice will provide more information. If you use long query, then you can ignore some recognition errors in the document, and it's still okay. Yeah.
Why does that experiment make sense?
Which experiment?
That last one. What is the motivation?
You mean in this experiment?
Yeah, without taking.
Yeah, because we don't have any experiments in long query and cross-lingual information retrieval on syllable lattice, so we just want to test on the syllable lattice on this task. So, but actually, we still have some problems we investigate. So after the workshop, we still find some approach to improve the syllable lattice.
And I guess another interesting finding that we stumbled upon when we were doing lattice is we try to, of course, weighting counts a lot. And we have a slide. I was trying to find that slide to show you for every crisscross, and if we're crisscrossing with a syllable that is actually wrong, we introduce more errors in our syllable diagrams because it's flat in our representation. So without acoustic score, it's going to hurt a lot. The other thing we tried also is whenever the May syllable recognizer disagrees with the Dragon syllable recognizer, and if we throw those chunks out and retrieve based on whatever's left of the document, we actually get an improved retrieval performance. So that's kind of funny, right? So when we think about that, what we think might be an explanation is perhaps something that may characterize spoken documents. When people want to speak or tell a story, and if it's content-carrying parts, maybe they speak more clearly, which is perhaps where the two recognizers will agree. And maybe they tend to disagree at places where it's noisy, so if you throw them out, you actually clear your documents of some unwanted corruption. I mean, that's a possible way to look at the problem. We don't know, I mean, it's at this point a conjecture, but we did see gain when we throw out chunks of the indexed documents where the May syllable recognizer disagrees with the Dragon syllable recognizer.
So that's, I think, a fair hypothesis, because one of the confidence measures that is used for words is consistency of a given word hypothesis across different hypotheses.
Right.
Which is what you're doing.
Yes. Yes. First.
I was a little confused. It looks like when you were training the May syllable recognizer, you used the alignment that you got from the Dragon recognizer. Seems like if you were trying to keep them orthogonal, you shouldn't use the output of one to train the other. I was confused why you did that.
Yeah.
Do you understand that?
Yeah. I mean, we have also considered, probably Shimin can tell you more about it. We have considered a number of options. In fact, the reason why we did that, as opposed to adopt our other approaches that we thought about, the reason why we did it this way is because the original goal was to say, well, from Dragon's word recognition output, we can only get one syllable string. Can the May syllable recognizer perhaps come up with some closed seconds and provide, and in cases where the closed second is actually the right one, then it can perhaps provide us with a gain by providing the alternate syllable hypothesis, which is why we try to proceed in lockstep with Dragon. And that was the original thinking until, before the workshop we saw how good Dragon's recognizer is. the other thinking is, of course, to move towards what you're saying. And there's a concept which we call content-based language modeling. I'll let Shimin tell you about it because it's his idea. Yeah, well, one of the ideas is to just let the May syllable recognizer run through and then train itself up from its original output. So it will settle on some state. Essentially, it's just throwing more data at the recognizer because we started out only having 11 hours of data. And in fact, because we chose to adopt that that approach earlier on, we were sort of forced to go that path. And we didn't really pursue this other path. But we did try to go somewhere closer to that place whereby later on we actually generated a lattice where with the improved acoustic models based on the May syllable recognizer, we ran through all the audio in TDT 2 and 3 without consideration of the word boundaries. So as long as we know the sentence boundaries, we ran it through so that our the May syllable recognition outputs are more different from the Dragon syllable recognition outputs. And that provides a very, very minor gain, and it's not clear whether that's significant or not. And so that's one thing we tried. Yeah, Charles?
Well, this is very impressive work that your team has done this summer.
Thanks.
I was very pleased with all that I saw. I wonder if you have any thoughts about trying to apply this to any of the standard TDT techniques. Any of these refinements that you've come up with. Consider that possibility.
Yeah, we'll certainly consider that possibility. You mean in the TDT 3 task? That was. Okay.
We're going to run this in topic tracking in TDT 2000.
Wonderful. Will it be called University of Maryland or will it be called the May?
No, we call it May.
University of May.
That way we don't have to change the act.
How hard is it to flip this system? You have queries in Mandarin and recovery of.
You just change the directions of the arrows.
It's
Is building something like that easier starting from here or just starting from scratch?
you mean using Chinese queries for English documents?
Yeah, going the other way.
It flips the problem really. I mean, I personally, I feel that's a lot of work. And it changes the original motivation towards our subword, adding subwords to the word scale. Because subwords were considered to be appropriate for Chinese.
No
Yeah.
difference, but does any part of what you've done transfer to the other tasks?
Yeah, so the entire word-based system transfers. It doesn't really care which direction you're going, although you have to do some different work.
In fact, it transferred. The entire word-based system started out as an English to Chinese, Chinese to English translation.
This is the first time we've ever done matching in Chinese. We've always done matching in English with queries that were coming out of Chinese, or moving the documents or whatever, but matching in the English space. And that transferred quite well. That was a couple of weeks of work to get all the resources lined up right and get all the hex codes and things like that. But once it's done, it transferred. You could do Japanese now the same way. You just put in an appropriate segmentation for Japanese. The subword issues do exist in English. I mean, I made the case, tried to make the case, that multi-scale indexing, it's actually done in English information retrieval. People index words and phrases. That's multi-scale indexing. And we found in Chinese it was very natural to use characters. It's one of the really delightful results of this workshop was that I don't think we would have thought, having worked at the word level, to do that. But it was just a very natural thing to do when we were focused together at the subword level. So would 5 grams work well in English? I mean, 5 grams in English are sort of the counterpart of bigrams in Chinese. We don't know. It's an interesting question. Right? But we might see that same gain if we just flip things around and used English 5 grams. One of the problems is there are very many more English 5 grams than there are Chinese bigrams, so you run into some efficiency considerations in trying to answer that question. But there are ways to slide the window by more than 1, for example, to make up for some of that. Oh yeah, someone had a question about evaluation, and we said, no, that's too hard a question. We'll answer it later. Anybody remember what it was? Good.
Lynette?
Yeah, actually, two quick questions. Actually, Doug, you said something that puzzled me. K.L. Kwok did a lot of work using bigrams on Chinese reviews. That would have been a very obvious kind of thing to use. I mean, I gather you got at this from a different direction. I mean,
So when you
why was it surprising?
Yeah, so when you translate, words are a natural unit for translation. I'll give you an example. I'll give you something that sort of happened to us along the way. It's one of Pat's lovely, this didn't make any sense to do, but we did it anyway, and it worked. The idea of structured queries says that you should estimate from the translations the statistics of the original term. And of course that makes sense with words, but it doesn't make sense once you break the words up into n-grams and you say from the statistics of the n-grams that are inside the words, we're going to go back, agglomerate them all together as if they were different translations. They're just the first half of the second half. And so we put all that back together, and we actually saw that under some conditions, we still preserved a gain. And so we spent a lot of time trying to explain that. And we actually can explain that now as to why this technique, structured queries, which had never been tried at the subword level, at the n-grams, would have a potentially beneficial effect. And that's something, if we hadn't been working at this level, we wouldn't have thought of, because we were working with systems that were tuned to words. And translation is naturally tuned to words until you start thinking about subword translation. As I said, I don't speak Chinese, but we, of course, speak Chinese a lot in the group. And I can actually tell what people are talking about. Every time they say Fred Jelinek, it sounds exactly like Fred Jelinek, right? Except with a little bit of this phonetic transcription into Chinese. So there's actually something there that got us started. And once we got going down that path, then we started asking questions about, after translation, can we be in subwords in meaningful ways? And we tried all the meaningful ways we could think of. So K.L. Kwok had done monolingual work in Chinese. But nobody thought before, at least that I knew of, about how to move across the language barrier at the subword level and then retrieve in subwords. So that's what got us started anyway.
The follow-up question is, should some of these techniques also help on simply on the text-based processing as opposed to the SDR?
Okay, so I'll say something about that, and then I suspect Helen will have something to say about the cross-language phonetic map, which needs a little bit of adaptation, but not much, and has been tried on the text-based level a couple of times. So the first thing is that the n-gram issues are entirely text-based. Those things we should be able to go home and do that tomorrow. They work on the anchor scripts. I mean, they're fine. It's a good idea. The second thing is that one of the results that we have not highlighted, but it's not a stunning result. It's just we didn't have the answer before. Is that everyone compares with this bogey of unbalanced translation. You know, you throw in all the translations and you say, and here, my technique is better, because of course the first technique was really stupid. And so Pirkala's method, the structured queries, are better. And balanced translation, an idea that two teams, Maryland and BBN, tried at TDT3, is also better. But no one had ever compared those two. Well, it turns out that those two give statistically indistinguishable performance. In fact, the first example that I gave of those two things that both came out at 0.4, it was those two things. That was structured versus balanced. And no one had ever compared them directly before. Now, it turns out that structured, which was previously thought to be the best known technique, takes 8 times as long to compute as balanced, because you're doing all the re-estimation of the statistics. So the balanced is much faster, and we're there now. So there's another one that transfers directly. Furthermore, the balanced transfers directly to n-grams in a way that structured doesn't transfer as well. So we can actually do better with balanced, and all the numbers here that are good are numbers off balanced. So there are several takeaway messages that work on the text level, and then Helen has something to say about cross-language phonetic map.
So, in fact, the way we have designed our cross-language phonetic map is such that, if you remember, we went through going from the English translation down to the English pronunciation down to the Chinese pronunciation in terms of syllables. Now, the way we get syllables is actually used by using a syllable diagram language model. As I mentioned, we borrow from the lexical access, the methodology we use for lexical access and speech recognition. In fact, I have a slide here which attempts to illustrate it's easy for us to substitute a character bigram in here for a syllable bigram. So if you remember, our example was Christopher. And if we had substituted a character bigram in here, we would be getting characters out. And those will be, so let's see. In fact, it's sort of swapped. The yellow one is this one, 叽哩西特夫, and then this one is 克里西托夫. And in fact, both are Chinese transliteration in character form of Christopher that one can see in Chinese newspapers. Yeah. So to that extent, we believe that the CLPM approach should be applicable to text. You first descend to the phonetic level, and then you try to emerge again at the text level.
I have a question. To what extent do your methods compensate for inadequacy of technology? In other words, when we have better technology, will we do it differently?
That's a good question.
When I say technology, for instance, speech recognition technology, where do you have to make the compromises because speech recognition is not perfect? Maybe you don't make any, I don't know.
It's not so much as speech recognition is not perfect. Speech recognition is not going to get perfect to the point where we need it. As in, if a new name comes up, I don't know, Putin. 5 years ago, nobody would have known Putin, or maybe 10 or some years ago. And so something like that, no recognizer is going to get.
Well, that's not true.
Meaning it will always get...
A human being has some kind of ideas how a Russian name could be spelled, so even when I hear it for the first time...
Right, no, but the point is that the orthography might actually come out wrong. I might spell Chernomerdin differently from you, but the sound sequence we associate with it is the same. So in a subword system, we'll always win with perfect speech technology, whereas, in other words, even with perfect speech technology, you would still want to do this. And this is just a...
I wasn't criticizing anything.
No,
I was wondering
saying
whether, in fact, we have here invested in everything that will always carry over.
Some parts, yes. I feel the
So
CLPM
what will
will
not carry over?
Oh, I can speculate that the confusion stuff that we do about confusable syllables or the syllable lattice may not if we had perfect recognition. But
I think I could give you an example. Even the speech recognition accuracy is 100%, and sometimes you still cannot retrieve what you want. For example, if you want to use a, let me see, it's a spoken query to spoken documents, then I say, I want a story about Kosovo in Chinese. And actually in Kosovo, in Helen's example, he has shown that Kosovo can be translated to at least 5 different character sequences. And the pronunciation is very similar, but not the same. Even the syllable is not the same. So even the recognition accuracy is 100%, and some document that use different character sequence, you just cannot retrieve. So this is why syllable approach is very useful for some tasks.
But it seems to me that even in text-based you have a problem with Kosovo, right?
So
because you can't take the article which has the Kosovo as the correct spelling of Kosovo. You still have to go back to figure out what the ultimate spelling somewhere else might be.
This is why I mentioned earlier that even the text-based retrieval syllable approach gives you very compatible performance.
So just to finish this up, there are 3 different, there are 3 different technologies involved here. We've talked about the speech technology and what would happen if it became perfect. You could equally well ask what would happen if the translation technology became perfect. And the answer there, I think, is that it would change everything that we do, that we're in fact covering for a lot of weakness. You know, our lexicon doesn't know what a verb is. So we could use a lot of help from natural language processing to do better, but the problem is that if you get a lot of help from natural language processing, your resource requirements go up, so the difficulty of porting to a new language goes up, and you become more brittle at some point. If you put in everything you know a lot only about a very little. So if you want to be very broad, you'll have relatively low performance. That trade-off won't change, but the points will move. And when the points move, some of the covering technology that we put in will likely change. Now, the third technology here is retrieval. And the fundamental retrieval has two fundamental problems. One is all we're doing is counting words. And so maybe you can do better than that, but you have this same breadth versus quality problem. The other problem with retrieval is that people just don't know what they want. So as soon as you can fix the human problem, so people will actually ask for what they want, and they'll agree that this is what they wanted when they got it, the relevance assessments, then you could get to 100%, but right now you can't get above 80% because the judges don't agree at that. And as you saw, there's this tremendous variation across exemplars. The variation across queries given by humans is worse when they give you 3 words, right? If they say Kosovo, what are they interested in? Right? I don't know anything to do with Kosovo. Something about a war in Kosovo, something about parents from Kosovo, I don't know. So there are these 3 technologies that all will move.
Just to follow up with this name business, it sounds as if all of the techniques that you've been using have really been addressing either the name recognition problem, the name translation problem, or name orthography in the variants of names. If we had these things perfect, would this technique have helped on other things, or was this really focused on the proper name problem?
I'll say a word and then maybe others will have something to say. The technology does not just work with names. It works with domain-specific technical terms, particularly terms in the computer industry, recently coined terms. There's a lot of motion across languages of terms. So to think of it as being applicable just to names, I think, is to be a little bit overly restrictive. Names, on the other hand, and domain-specific terms and recently coined terms turn out to be tremendously important search terms. So if you looked at the list that Gina had put up, which isn't up now, but of the list of the terms that were out of vocabulary, and then you said, which would you rather have, these 1,000 or the other 11,000 as your search terms? You might go for those 1,000.
Yeah, I share the same view as Doug on that. The fact that we use names throughout our examples in this presentation is mainly because actually we're using names to illustrate the effect of out-of-vocabulary words, be it in translation or in recognition. And a lot of times it's names, but there are other times when they're not names. And you know, it's to find the best way we can to handle those, that unknown piece of information that we believe it's probably going to be crucial for retrieval. Yeah.
This concludes the morning session.